In this video, I'm going to show you how to find the domain and range of a transformed ln function. So there's a three-step method I like to show my students which helps deal with this. So what you should be aware of is the graph of ln x. And in case you aren't, I'll just show you right now. So it looks something like this, and it gets exponentially, or well, you can say that as the x values increase, it increases but at a lower rate, as you can see here. Now, another way to remember it is knowing that if you if you know the function e to the x, that crosses the x-axis at 1, and if you reflect that in the line y equals x, you're going to get the ln x function, because e to the x and ln x are what we call inverse functions, and when you reflect a function and it gets you to another function, those two are inverses. Sorry, I don't know why I'm stumbling over my words. But the key things to take away from this function is that it never reaches 0, and so it's never less than 0 either. So the domain, the set of possible x values for this function, is where x is bigger than 0. The range, however, because it does continue increasing and increasing as x gets larger, and the y value gets smaller and smaller, more and more negative, as x gets closer and closer to 0, although it never touches 0, we can say that y has an unlimited amount of values. We say that by saying that it's in the set of real numbers. That means that it can be any real number, whether it's rational, irrational, it can be positive 3, positive 3.5, positive pi, negative pi. If you get what I mean, it can be anything, rational or irrational. Moving on now, we're going to talk about what happens when you transform this. So let's call this g of x. To make it relate to our graph here, I'm now going to replace the bracket of x with x plus x minus 3, sorry. So we do that by representing g of x as g of x minus 3. That is what it would equal ln of x minus 3. Now what does this transformation do to the previous graph on the left? It moves everything 3 units to the left. That means that the asymptote, instead of being at where x is equal to 0, is now going to be where x is equal to minus 3. So let's label that. Oh, sorry. I made a little mistake. When you deal with the inside of a bracket, it's the opposite transformation that happens. So although you can make a mistake just like I did of moving everything 3 units to the left, you actually move everything 3 units to the right when it's a transformation inside the bracket. Sorry about that. That means that the asymptote will now be, instead of x equals 0, it moves 3 units to the right. So it will be at x equals 3. So it will still have that same shape, but everything would be shifted 3 units to the right. Now here, it would cross the x-axis at 1, but now it's going to cross the x-axis at 4, because everything's moved 3 units to the right. One more transformation to make it match this expression here, we're going to add 3 to this. So 3 plus g of x minus 3 is what would get you to 3 plus ln of x minus 3. So how do we apply that transformation? Well, what this does is it adds 3 onto all the y coordinates. That means that this coordinate 4 will just move up, and it will be 4, 3, if that makes sense, instead of 4, 0. So our graph will look pretty much the same in that it's just everything will be lifted 3 units up. I guess you can just show that it crosses the x-axis before when x is equal to 4, because that's how its nature will be. But you don't really have to represent that. All we're representing here is the domain and range. Let's think of all the possible x values and all the possible y values that we can put into this function. Well, the domain now, we know x can't be less than 3, because we've established that from before. It can't be equal to 3, so x has to be greater than 3. The range is all the y values that this function can have. Now, as x gets closer and closer to 3, like as it's 3.0001, if you put that into your calculator, you'll even notice that it's going to get more and more negative, but it never reaches a fixed point. Similarly, if you put a very, very large value of x into this function, you'll see that it keeps on increasing and it never reaches a set point. So we say the y, the range values is in the element of real numbers. It can be any value itself. And that's how you can find the domain and range of a complex function like this, by breaking it down from functions that you already know how to deal with. Hopefully this video helped in dealing with this. Be sure to leave a like if it did, and subscribe. I'd appreciate it a lot. Thanks for watching. I hope this video helped. If you have any tutoring inquiries, be sure to visit my website, www.excellineducation.co.uk. It's on the first link in the description too.